sorts of exotic topics, and he will talk us through some of the quantum aspects of Einstein's theory.
Thank you. Good afternoon. I hope you had a nice lunch and you had time to digest all you learned about general relativity. Because now I will talk about quantum aspects of Einstein's universe. But before that, I will need to tell you something about quantum physics. And you see, until the end of the 19th century, what scientists were studying is what we call classical physics. It's physics that relates to phenomena that are very close to our everyday experience. For example, Newton's law, well, they can describe how an apple falls from its tree. Now, this morning you learned that when you approach the speed of light, or when you are in the vicinity of a very massive object, such as a star, well, then classical physics is not, starts to fail, right? And you need to use general relativity. Time and space merge into a space-time. Clocks start to tick at different rates, and space-time itself becomes curved. And this is very important, for example, to study the evolution of the universe, but it has also practical applications, as we saw in the GPS system. Now, while Einstein, during more than 10 years, was developing all his ideas, there was another revolution going on. And the story of this revolution is much longer than the story of relativity. And it took many people to work on it and contribute with ideas. And many of them are in this picture taken at the Congress of Solvay in Brussels. You can notice that Einstein is there, so he also contributed to this other revolution. And the other thing that you can notice is that there is only one woman. Can you spot her? She's here. It's Marie Curie. She's the only woman, but she's also the only participant with 2 Nobel Prizes in her Now, to tell you this story, I will need the help of a special mailbox. And we will receive postcards from these scientists telling and illustrating their ideas for it. And the first postcard we receive is a postcard by Gustav Kirchhoff, and it's dated 1859. Kirchhoff at the time was studying the radiation, that is the light that comes from the sun. He was just splitting it using a prism and looking how much of this light is in each color. Okay? And this made him think, and he made a big discovery. Take a black body. A black body is simply a piece of matter that perfectly absorbs any incoming radiation. And think of a charcoal, for example. And then heat it up. It will emit some light. Your charcoal becomes red when it's hot. Now, what he discovered is that the light that it emits, this black body, is universal. This means that it doesn't depend at all on the nature of the material it is made of. It only depends on the temperature it has, okay? Only on the temperature. And this, well, and to reach this conclusion, he had to resort to the second law of thermodynamics. Now, don't be misled by the second in the name. It's a very important law. It's the reason why perpetual motion machines cannot be built. And already in 1500, Da Vinci knew that it was a holy grail that you could not obtain, and with contempt it was saying, leave this to alchemists, right? And more recently, Eddington, the same Eddington that measured the deflection of light during the solar eclipse of 1919, said that the second principle holds the supreme position among the laws of nature. So what does this second principle of thermodynamics say? Well, it has many formulations, but one of the earliest, and perhaps the simplest, is the one due to Clausius. He said, he said, take two bodies, that is, two pieces of material, one that is warm, hot, and the other one that is cold. Then heat will spontaneously flow from the hot one to the cold body. You know it, if you leave your drink in the sun, it will become warm, and ice cubes will melt, right? And also, if you want instead to make your cold body colder, and transfer heat from the cold body to the hot body, you need to perform work. That's why your fridge needs electric power to work. Now, it's possible, it looks like a very simple statement, right? But it has deep ramifications and many consequences. And what Boltzmann understood is that one can make it very quantitative, this second law of thermodynamics. So imagine I have a box with some gas in it. Huh? For example, the air in this room. And you ask me to describe this gas. Well, I could start to tell you the exact position and velocity of each of the molecules that compose this gas. But you wouldn't be much wiser with it, right? Instead, I could give you three numbers: the temperature, the pressure, and the volume of this gas. And now you probably know everything you want to know about this gas. So you see, there are two different ways of describing a system. One is to give the detailed information about each of its constituents. We will call this the microscopic state, okay, or microstate. And the other one is simply to describe its general aspect, its macroscopic properties. Okay? Sure, when I give you the macroscopic properties of the gas, I'm losing some information. I don't know exactly where each of these molecules is. But I don't really care, right? Because, you see, there are many, many of such configurations that will give you exactly the same temperature, pressure, and volume. If I move some molecules here, I'm not changing the temperature of the air in the room, right? Now, what Boltzmann understood is that if you count all the different microscopic configurations that give you the same overall properties for your gas, then this number is related to something that physicists at the time were calling, and we still call, entropy. And you can formulate the second principle of thermodynamics, or the second law of thermodynamics, by saying that entropy can never decrease. Now, this is a very special kind of law. You see, in physics, usually laws tell us that something cannot change. The entropy is, the energy is conserved, or the number of atoms that make this object remains the same over time. Or maybe it's an equality, like the Newton's law that makes a relation between force and acceleration of a body. But here, no. So usually, laws of physics do not distinguish future and past. Okay? But here we have a law that tells us that something can only increase. So it's able to differentiate between past and future. Look at this glass. It's intact. Every single piece of it has a precise spot in it. Okay? So the entropy is small. But when I break it, all the pieces can be scattered around in many, many different ways. The entropy is very high. That's why this glass, sooner or later, will break. And that's why you never saw pieces of glass just reconstruct a whole glass spontaneously. Now, let's go back to Kirchhoff. We said that Kirchhoff understood that the radiation, the light emitted by a black body, is universal. And this set a big challenge to physicists at the time, both experimentalists that had to measure how much light of each color was emitted by this black body, and by theoretical physicists that had to compute this amount of light in each color from first principles. And it took 40 years to find a solution. And indeed, the next postcard is from Max Planck, and dates from 1900. And what he understood is that there is no way, using only classical physics, to solve the black body problem. You need something more. And this something more was his postulate, his quantum hypothesis. He had to assume that energy cannot be exchanged in arbitrary amounts, but only in tiny packets, tiny amounts that he called quantum. And then so essentially it's a bit like the memory of a computer. Internally, a computer can only store information in bits. The bit is a quantum of information. It's either 0 or 1. It can never be a number between 0 and 1. And here it's somehow the same. And like this, Planck managed to reproduce perfectly what experimenters were finding. But he always thought of this quantum hypothesis as a clever mathematical trick. It took Einstein 5 years later to understand that quanta are real. Light itself is made of quanta of energy, small packets of light. And these small packets of light, these are what we call today photons. Now, this quantum hypothesis gave an immense power to physicists. At that point, they started to calculate a lot of quantities and understand a lot of physical systems. And indeed, our mailbox now starts to be overwhelmed by the postcards that arrive. I will not have time to show them all, but for example, Bohr, he wants to tell us about his atomic model, where electrons orbit the nucleus. De Broglie would like to tell you that particles sometimes behave like a wave. That's really strange. And Schrödinger, he calculated the motion of an electron in an hydrogen atom. And he found something very strange. He didn't find a precise location of the electron. What he found was these cute little flowers. We call them orbitals now. They describe the probability of finding the electron somewhere. Sorry. They describe the probability to find the electrons somewhere. And the higher, the whiter the color, and the higher the probability is to find the electron there. And the weirdest thing was that, well, this probabilistic answer was not due to our ignorance. It was really how the electron behaves. And to explain this better, Heisenberg invented a thought experiment. He was saying, well, imagine you have a ball that is coming to you. Okay? Well, you see it, you know where it's going, and you will be able to catch it. How does this work? Well, some light from the sun will bounce on the ball, and from the ball it will reach your eye, and you will know where the ball is, and you will estimate its speed. So why don't we do just the same thing with an electron? So imagine to shoot an electron with a particular velocity. And then you send light, photons, towards this electron, and at some point one of these photons will bounce on the electron, and then by just measuring this electron, you will know exactly like you knew where the ball is, you will know where the electron is. Well, you see, the ball is very heavy, very massive, and when it's hit by these tiny little photons, it doesn't even tickle it. But the electron has a very tiny mass, and its mass is comparable to the energy of the photon. And therefore, when the photon hits the electron, and bounces on it. It also kicks it. Congratulations. Now you know where your electron is, but you change its velocity. So in a few seconds, you have no idea where it will be. This led Heisenberg to formulate the famous uncertainty principle, which says that it's impossible to determine accurately both the position and the velocity at the same instant. Now, this is very counterintuitive, right? Because we are used that everything has a position and a speed. When you sit in your car, you know where your car is and you know at what speed your car goes, right? And even Einstein had a hard time to accept it. And it did during the Sorbet conferences in 27 and 30 and the 30s. They were all in the same hotel. And every morning Einstein would arrive with a new thought experiment that he could use to overcome the uncertainty principle. And then Bohr would think about it during the whole day, and by dinner he had an answer and he would show him why he doesn't work. And then one day, Einstein thought he had the killer experiment. And this put Bohr into trouble. I think this picture must have been taken more or less at the time. But then Bohr thought a lot about it, and he managed to find why this experiment failed. And the why included Einstein's own general relativity. At that moment, Einstein had to capitulate, and he had more or less to accept the uncertainty principle. Now, you see, to measure a velocity, you need to measure time, because the velocity is miles per hour, right? And also, the faster you go, the more energy you have. So it's quite natural that there will be also an uncertainty linking energy and time. What does it tell us? Well, it tells us that if we want to measure an energy, it takes time. And the more accurately we want to be in measuring this energy, and the more time the experiment will take. As a consequence, energy fluctuates. Energy can just appear out of nothing, a tiny bit of energy, and for a very short time be there, but then disappear before we had time to measure it. And this is perfectly consistent. And also particles, sneaky particles, can appear out of nothing, live for a very short time, and then collide again and destroy themselves. But if they do this fast enough, we will not have time to see them. Did I? That was one of them. So take the vacuum. Vacuum, well, there is no energy, no particle, no nothing. However, if you look at microscopic scales and you take into account quantum mechanics, there will constantly be pairs of particle, a particle and antiparticle, that are created out of nothing. They live for a short time, and then they go back in the same point and get destroyed. This is quite strange, right? But it had, for example, a very important role in the early universe. However, I will not talk about this today. I will talk about why this is important for black holes. Okay? But before getting to black holes, let's summarize a little bit what we learned about the quantum revolution. First of all, the light emitted by a black body, is universal, and it depends only on its temperature. Then we have the uncertainty principle. We cannot measure accurately both position and velocity at the same instant. And as a consequence, the vacuum is not a boring place at all. There is constantly all these particles getting created and destroyed everywhere. Now, these things are extremely important because without them, we wouldn't have the transistor. And without the transistor, we wouldn't have all the electronic gadgets and devices that we use daily. Nowadays, scientists, they use and Skype to communicate. But 100 years ago, they didn't have emails and Skype, and it's really with postcards that they were communicating, right? This is a postcard that Albert Einstein sent to Hermann Bayer, describing some of his findings. But back to classical physics. Remember we said that if you have a large mass, while classical physics fails, and you have to take into account general relativity. And now we just learned that classical physics fails also when you go on the atomic or subatomic scale. Now you could wonder, what if I take my huge mass and I squeeze it in a very small subatomic space? Okay. Then I have to take into account both general relativity and quantum physics. And you might wonder how small I must go for these effects to be really important. And the answer is very tiny. Right? So here I put some length scales in meters. Wikipedia tells me that the average height of a human is 1.7 meters. And then you can see that you have the Mount Everest at 8,000 meters, 6 million meters, the Great Wall of China, and so on and so forth, up to the diameter of the universe. This is a huge number. It's 87 followed by 25 zeros meters. That's essentially the time it takes for light. It's the distance that light reaches in 13 billion years, which is the age of our universe. And we can go in the other direction. So we have ants, blood cells, and atoms, and going down, 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 we reach the Planck scale. The Planck scale is where it is unavoidable to use both general relativity and quantum theory to describe the physics. And it's incredibly tiny. It's 0.3401. It's way smaller than the smallest distance we have ever seen. At CERN, at the Large Hadron Collider, this big accelerator of particles, well, we see lengths that are very tiny, but are still 1 million billion times bigger than the Planck scale. So this Planck scale is completely out of reach for us. Well, in some cases, quantum gravity effects where general relativity and quantum theory are important, can become apparent also to us. And it's essentially in two cases. First of all, as I said before, shortly after the Big Bang, and the other case, and maybe as we were saying before, maybe this, well, who knows, maybe in the next generation of gravitational wave detectors might see something there. And then close to a black hole. So you learned this morning that black holes are collapsed stars with a gravitational attraction that is so strong that nothing can escape from them, not even light. And you also learned that for a long time nobody believed that they existed, even though the mathematical solution describing them was there since the start of general relativity, right? So Schwarzschild in 1916. It's only in the 60s and 70s that a lot of people started to work on them and discover their properties. And the first property I want to talk about is, in the words of John Wheeler, that black holes have no air. What does this mean? Well, it means something very simple, actually. If you take a black hole and you tell me its mass, its angular momentum, this is how much it spins, and how much electric charges it contains, you have completely characterized your black hole. You take two black holes that have the same mass, angular momentum, and electric charge, there is no way, according to general relativity, to distinguish them. There is no detail, no hair there to say, oh, he's blonde and the other one not, right? So black holes have no hair. They're the simplest objects in all of physics, and they don't care about how they were formed. You can form one by throwing radio sets and TV sets, or by throwing elephants. But once they've been swallowed, all the information about the TV set of the elephant has disappeared. And only mass, angular momentum, and charge remain. So let's go back to Boltzmann and remember how he was describing his system microscopically. He was saying, well, our system, we can describe it also by giving the exact position of all its constituents. But the black hole, once it's formed, it has no more constituents. It erases all the information. There is only one microstate, one microscopic state that gives this mass, angular momentum, and charge. Therefore, black holes cannot have any entropy. This was troubling Wheeler, because he was saying, well, but if this is true, take my box of gas before, okay? In this box there is a lot of entropy. Throw it into the black hole. And now, poof, it disappeared. So I lowered the entropy of the universe. And I violated the second law of thermodynamics. This is, well, it's very worrying. Another important discovery was made by Stephen Hawking in 1970s, and it's called the area law. Essentially, it only says that black holes can only grow. It's natural. They just swallow everything you throw at them and never let anything get out of them, right? However, what he noticed is that it's not the mass of the black hole that increases. What increases is the area of the horizon of the black hole. The horizon, the event horizon, is the surface of the black hole. It's this point of no return that once you pass it, you're swallowed by the black hole and you don't get out. And this area can never decrease. This is another one of those strange laws of physics that are not conservations or equalities, but tell us about past and future. Where the area is larger, it's the future, and where the area of the black hole is, when the black hole is smaller, is the past. So this inspired Bekenstein. He was a young student of Wheeler, and he said, well, but then it's obvious, black holes have an entropy, and this entropy must be essentially given by their area. Okay? And like this, if I assume this, you can see that you can save the second law of thermodynamics. Because if I throw my piece, my box with gas and entropy inside it, it will not disappear, but somehow it will be encoded in the black hole, and the black hole will still have this entropy. Now, physicists at the time were not convinced at all. And later that same year, there was a congress in Leuch that lasted 1 month, and everybody convened there. It's a very nice little town just under the Mont Blanc, which is, I don't know on which side, in the French Alps. And one of the participants of this congress was Hawking, and there were also James Bardeen and Brian Carter. And together they started to calculate, and they found what we call the laws of black hole mechanics. These laws simply describe how a black hole evolves. However, when they found them very familiar. What they noticed is that just by changing some words, you would obtain exactly the laws of thermodynamics. If you take everywhere you have in this equation the surface gravity, you substitute it with temperature, and the surface gravity is simply how much attraction you feel when you are very close to the black hole. And if you substitute the expression area of the horizon with entropy, then the laws of black hole dynamics are just the laws of thermodynamics. But that had to be only an analogy, right? I mean, somehow people at the time saw in this the proof that Bekenstein to be wrong. And black holes didn't have entropy because, you see, if, as Bekenstein claimed, black holes have an entropy, then they would have also temperature. But remember, Kirchhoff taught us that any black body that has a temperature also emits light. And everybody knows that black holes, nothing can escape from a black hole, not even light. So it was not possible. And everybody agreed that Bekenstein had to be. However, remember what Eddington said before? He warned us. If your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation. Indeed, 2 years later, Hawking showed that, yes, this story is true, but only because we forgot to take into account quantum effects. Remember, in the vacuum, you have constantly particles and antiparticles that are created and destroyed. So he was saying, imagine your black hole. Outside of it you have vacuum, and you have pairs of particles getting created. And most of the time, they will just live for a short time and be destroyed again. But sometimes, one of these pairs will be torn apart by the tidal gravity of the black hole. And one of these particles will be swallowed by the black hole. And the other one, now it doesn't have any partner to be destroyed with. And it becomes a real particle by absorbing some of the energy of the black hole. And this particle will just escape the black hole and will be some radiation, some light emitted by the black hole. And at the same time, the black hole will decrease slightly its mass. So black holes are, after all, not that dark. They emit some particles, and Hawking calculated exactly how much energy was emitted in each colors of the light. And what he found was, again, very familiar. It was exactly the Planck law that described the radiation emitted by a black body that had a certain temperature T. So black holes are really objects that have a temperature and therefore an entropy. And by emitting this radiation, essentially they simply evaporate. Exactly like a drop of water evaporates if you look. Now, this is an extremely important result because, you see, we don't have a theory of quantum gravity. If we try to put together general relativity and quantum physics, they just don't match, okay? And we have some candidate theories, such as string theory, but we don't know what is the true quantum gravity theory. However, this result of Hawking opens a window. It shows us some properties that our theory will have to have. Okay? And I want to spend the last few minutes describing these properties. Okay? And the first observation is the following. Well, we saw that the entropy essentially tells you how many different ways of arranging the constituents of your body give you the same overall macroscopic properties that we saw. Okay. And Bekenstein told us also that the entropy of a black hole is proportional to the area. So somehow, all the information that is contained by the black hole is encoded in its area, on its surface. Okay? You can imagine tiny little bits, okay? They're of the length of the Planck length. Remember, it's very, very small. And for each of this little area, you can have a bit, a 0 or a 1. And this accounts for all the information that is in your book. Now, this is a huge amount of information, because this this cell is very, very small. Now let's forget for one moment black holes and ask a different question. Imagine I have a region of space, and I asked, how much information can I squeeze into this region of space? You know, I can take books, hard disks, and start to stuff them here and compress them and so on. What is the limit? Well, naively, you would think that you can go down until a little cube that has the side of this very tiny Planck length. And for each of those cubes, I can put a bit, 0 or 1. And like this, I can encode the information inside my region of space. So imagine we have a region of space that is, for example, 100 Planck lengths its side is 100 units like this. Then how many bits do I have here inside? Well, it's 100 times 100 times again 100. I can store in it 1 million bits. Well, wait, it's not that simple, because imagine I want to actually put these bits into this region of space. Every single bit has to be stored somehow. So it comes with some energy. There is no information without energy. And way before I manage to stuff here inside 1 million bits, there will be so much energy in this region of space that it will just become a black hole. And then if you want to count how much information there is in the black hole, you know that we don't have to count its volume. What is important is how much air, how big is its surface. We know the information of the black hole is stored on the surface. So let's take again this region of space and let's count how many bits I can store in it, on its surface. Well, this is the surface of the cube, okay? And now we have 100 times 100 times 6 faces. That's 60,000 bits. That's way smaller than 1 million that we obtained before. So what is the lesson here? What did we learn? Well, we learned that when going to small scales, there is a fundamental limit on how much information you can put on this region. And at the same time, we learned that if you have a region of space, actually, it's more efficient to describe what is inside this region by encoding the information on the surface of its boundary, of the boundary of this region, exactly like we did here. Okay? This is very strange, but it has led to what we call now the holographic principle. And Toft called it like this because it's a bit like this hologram that you have on your credit card. You see, when you look at it, it looks three-dimensional. It has 3 directions, right? You move your head and the picture moves. But all the information about it, it's just encoded on a surface. So this seems a fundamental quality of gravity when you go on microscopic scales. And it sounds very strange, but in 1997, 20 years ago, Juan Maldacena managed to build a mathematical model where for some special spaces, this is worked out, is realized exactly. Everything is described in terms of what you have on the surface. Now, these spacetimes are very special, and unfortunately, they're not the kind of spacetime we live in. So, what we did in the last 20 years is to... Now, however, you see, the fact that one can realize this mathematical model shows us that we are really on the correct path, I believe at least, that it's the right path to understand the properties of gravity at the microscope. And in the last 20 years, what we have done is try to extend this mathematical formulation and try to understand it, how to apply it to the real world. Now, unfortunately, our special mailbox I tried, but it doesn't send us any postcard from the future. Maybe you will understand why in the next episode. So I have to finish the story here. Thank you.
So, do we have any questions for Michael?
I hope I...
Well, I'll ask a question, and I haven't a clue what I'm asking really, but what is the past history of entropy in the universe and the future? I mean, people talk of heat death of the universe and so on. That was a common thing to talk about some time back. But what do we have as a future for the universe in terms of entropy? And
well,
what was the history as well of entropy in the universe?
Well, I'm not a cosmologist, so I'm not sure I will answer it. Well, I know that many people have different ideas on this. But essentially, the entropy of the universe has been constantly increasing. And indeed, stars, by burning their nuclear fuel, they're just producing more and more entropy. And a black hole, I didn't show you the numbers, but you can imagine the size of this bit is extremely small. The amount of entropy that there is in a single black hole is huge. And what will happen is that most of the matter will collapse at the end into black holes, and what will remain will be just radiation with very high entropy. So yes, then I don't know exactly what will happen in the future. It looks like, I mean, from what we understood now, that we have a positive cosmological constant, and this means that the universe started, well, recently in a cosmological scale, to expand at an exponential scale, at an exponential speed. And this will cool down everything very, very fast. And so, yeah, I think eternal death is very likely.
Are these based on the need for quantum ideas, these arguments, or is that essentially...
No, the cosmological constant, so the fact that the universe is expanding and will expand forever now, is really observational. We know now that there is a positive cosmological constant, the universe is expanding, everything will end up to cool down and be in a very high entropic state.
Can I ask, if they have started to talk about space being quantized, does that mean that there's a finite amount, or could it expand forever? I mean, you're talking about infinity, and yet you're talking about quantization.
Well,
they do seem to be paradoxical.
Well, the fact that it's expanding, it's just a cosmological fact, and it doesn't have much to do with the fact, with the quantization, because it's on a large scale, it's on astronomical scale that we see it expanding. And there, general relativity works very well. You don't need quantum physics to see that.
But what are you saying is expanding? Is it matter, or is it space?
Oh, it's space-time itself.
It's space. So space actually has got a characterization, or it has some sort of nature.
Yes, it's, you know, I don't know if you saw during the lunch break this rubber sheet they had there. And the fabric of space-time is really like this. It can stretch and expand and contract, and that's what the gravitational waves they saw are, right? The space that contracts and expands. And on a cosmological scale, it's just expanding, but on an astronomical scale, it's just not just a radical, but it's difficult to imagine, right? It's the whole space that is expanding.
Would you say then that space is infinitely visible. As
Well,
Leibniz wanted it to be.
Well, exactly like in quantum theory, where we see that energy, for example, of light is quantized and it comes in tiny bits. We don't have a theory of quantum gravity now, but everything points to the fact that if you go to very, very small distances, space will look very different from what Einstein told us, right? And probably there is some minimum distance, some let's say fundamental bit of space-time that if you try that you cannot go further, or at least it will not have a geometrical description like we have of ordinary space, right? It will need some different mathematics to be described.
And we only have, can I just ask you, do we have quantum space in respect of closed strings? Loop. It's loop quantum gravity, isn't it?
So loop quantum gravity and string theory are completely different things. They try to do the same thing.
Okay.
They try to. It's you're right to be a little bit confused, because indeed strings they can be closed. So strings are. Look at them. I don't know how.
Yeah.
So in string theory, instead of having particles that interact, and the problem of particles is that they can go arbitrarily close to each other. Instead of having particles, which can be electrons or quarks or whatever, we have little strings. And these strings will vibrate. And according to the frequency at which they vibrate, they will be a different particle, for example, an electron or a quark or something else. And the closed one like this, some of them, if they vibrate with the correct frequency, they will just be gravitons. And gravitons are what we believe the equivalent of the photon for light, right? But for gravity. That is the tiniest amount of gravity wave you can have. Also light is a wave, right? It's electromagnetic, it's an electromagnetic wave, light. Okay? But if you go on atomic scales, you see that it's made of small corpuscles, small particles, the photons. Gravity is the same. Before you heard a talk that they just now saw gravitational waves. Well, we have reason to believe that the tiniest one will not be arbitrarily small, but it will be small packets which are graviton, exactly like the photons. Okay. And in string theory, you describe them in this way.
These would be wrapped up as tiny little enclosed kind of parts of a larger three-dimensional space. And could you have one tiny, tiny three-dimensional inside a larger until you get to the microscopic size, and then you would have 9 dimensions with time being expressed in the...
Well, indeed, string theory to be formulated needs more dimensions. So it's like if we were, imagine our 4-dimensional space-time, that is three-dimensional space plus 1 dimension of time that is given by the surface. So we live here, right? But then, you know, imagine an ant that lives on this blackboard. For the ant, this is just the whole world. It doesn't really know that there is one more dimension. And string theory indeed predicts something similar. It's actually one of the difficulties of string theory, right? Because everybody knows we live in 4 dimensions. So if string theory is right, well, we have to understand what to do with all those extra dimensions.
So this is our interpretation of a mathematical model which we've devised to explain all this. I'm not sure I think it's really sorry.
Okay, so if we take a break for coffee, and if we come back at